44. 44. Okay. We had a similar problem in class. And let's look at 40, which is the same idea. So limit as x approaches 0 from sine 4x over sine 6x. For this particular one, we can use L'Hopital's rule. Is not going to be difficult. But let's say we don't use L'Hopital's rule. When I plug in, what do I get? Because I need to do that. I need to know what it is. Of course. Good, so there is hope. Very good. So I know that there is a limit that we studied a long time ago that requires all these three pieces to be the same for the answer to be perfect. Also, the reverse, the multiplicative inverse of this function will give us the same answer. As long as all these are identical, the answer will be 1. So therefore, I'm going to try from here to create that situation. So I have limit as x approaches 0 from sine 4 over x, sine 4x times sine 6x. This is just a simple algebraic manipulation, and of course, I cannot leave blank in here. So the question is, what do I need? Well, I know that when x approaches 0, 4x approaches perfect, and also 6x approaches perfect. So since I know that, for the example, for this one, I have a 4x, so I need to have a 4x, I'm allowed to multiply and divide by 4x. And that will take care of this portion, because 4x and 4x will be 1. I will repeat the same process for 6x. Because I can multiply the top by 6x and multiply the bottom by 6x. That will not change anything. But now what is the achievement is this. That I know that sine 4x over 4x, when 4x approaches 0, must be. And then sine 6x, 6x at the top over sine 6x, when 6x approaches 0, must be perfect. So now what is left? A 4x and a 6x. But I will simplify by x. And I get 4/6, which is 2/3. So this is pretty similar to the other one. Just a simple algebraic manipulation will have that. Better?
Yeah.
Perfect. Anything else that you had questions about? Anything else you are working on? Just anything? Anything? Is there anything else that you would like to go back to? Okay, so the target is for today, hopefully we can finish chapter 3. We will continue with 3.10 and 3.11. These are the last two sections. For 3.11, we are only going to look at 3 functions and their derivatives. There is more in there, but that's all I need, 3 functions. And this will require almost the entire class today, 3.10. Although I would say not difficult, it requires time. We have to practice. It's not going to click right away. Okay, so let's start. The title for 3.10 is Linear Approximations and Differentials. Linear approximations and differentials. Okay. Now, I would like to go back for a minute to the problem that we looked at with the cost function. So the cost function was given to us. We were asked to find the marginal cost, we determined the derivative of the cost function. And then we were asked to determine, if you remember, C prime of 200 in that word problem some time ago. And then we were asked to find the exact change in the cost for a minor increase in x. So let me remind you, we don't need to go to the function, back to the function, but we were given C of x. We were asked to find C prime of x. And we were asked to find C prime of 200. C prime of 200, we said, predicts the cost of the 201st item. But the exact cost for the 201st item is C of 201 minus C of 200. This is the exact cost. So what happens here is this. At 200, there is a tangent to the graph of cost. When x is 200, there is a tangent line. If I deviate from 200 just a tiny bit, 1, not go to 300, but from 200 to 201, I will still be using this slope, right? C prime of x. It's not going to make a difference. So that's why what it's called the error, the C prime of 200 was so close to this difference. But now if I have that tangent at 200 and I want to determine the difference in cost if we manufacture not 201 but 300, do you think that if I plug in C prime of 300, will I get an approximate cost of the difference between C300 and the C200? No, because it's too far away. So for a minor change in x, I can still use the same slope. Okay, so this is the target now. We're going to work with this idea today. So let's graph a function. We're back to day 1 of this course.
Imprecise definition.
No, you'll see in a minute. No, it's the approximation. Okay, of course this is point P. And of course it has coordinate x and of course. And of course Q, our best friend, or P's best friend, Q. How far is this x from this x?
A very little bit.
Tiny bit. That this time we're going to change the notation. It's still that little h. It's still the same. But we need a new notation right now. Delta x or dx. So this is x plus dx or x plus delta x. They are the same. Now we're going to call this dx kind of an error. It's not an error, but we can assume it's an error. In x, of course. Or if you want a change in x, but minor change in x. That little h that we know about, but now we need a new notation. Okay, so now can anyone give us this?
X plus dx.
Perfect. Of course, please imagine that these 2 points are extremely close to each other. But if I don't zoom in, I won't be able to explain and graph anything. So these are very close to each other. P and Q are very close, like Nick and Joey, good friends.
I would say that.
Good. Okay. Yes, I would. I'm going to, of course, graph the tangent at P and extend it. Leave it alone for a moment because I want to present something before I conclude anything about that. So what is this difference?
X plus dx minus f of x.
Awesome. This is exactly like C of 201 minus C 200. For a minor change in x, this would have been C of 201 minus C of 200, correct? This is called delta y, and it equals exactly f of x plus dx minus f of x, and it is the exact change in y, or the function, triggered by, of course, dx or delta x change in x, of course. This is delta y. Okay, perfect. Again, from our example from last time, it's this difference. So if I change 200 to 201, this is the difference in cost. The exact difference. C of 201 minus C of 200. Perfect. So now I'm back to my tangent. I'm going to form a right triangle. This right triangle. I don't want to put more stuff in this graph, so I'm going to take that triangle aside on a different piece of paper. Here's the triangle. This is point P. This is clear dx. Now, can anyone give us the slope of this line? Of course. F prime of x is the slope of the tangent line at P, which has coordinate x, so it must be f prime of x at that point. Awesome. Thank you. Now, I would like to write f prime of x, which is the slope, in a different way. What is the other way that we've been using so far? There are many, many ways, right? We have a long list. There is. Thank you very much. Okay, so now forget about all this for a moment. And if I give you this triangle and I ask you, can you find the slope of this line? You don't know anything. You don't have any sides, nothing. The slope of this line, what will you say? It's rise over run, correct? So it's this height over, now I know this is dx. So what do you think this is then? Of course. But now you should be upset, at least appalled, and say, you told us that f prime of x is the same with dy over dx, but you never really told us that these two are totally different, separate quantities. They are. We didn't have to split this in two or talk about and split hairs, but now we do. So f prime of x equals dy over dx, but also in the context of this triangle, if this piece is dx, this piece must be dy. Now, what does dy mean? This is called the differential of y, which is not the exact change in y for a minor change in x. But what is it? Is the change obtained using the derivative. Is this. So the differential of y. So let's write this here because I have a question for you. Put the f prime of x over 1 and solve this equation for me for dy, because this is extremely important for chapter 5 and moving forward. So cross multiply and tell me dy equals?
Dx times f prime x.
Correct. The order will be this, however, but you're right. It doesn't matter. It's the same thing if you write dx times f prime, but we have to write it in this order moving forward. So the differential of y is the change in y triggered by dx, but measured using the derivative. And it's not the exact change. Okay, so let's come back. So since now we can imagine that Q is very close to P. And this piece now, can anyone give us this piece? Perfect. But now imagine one more time that Q is very close to P. Would you accept? This is huge here, but this is tiny, tiny. So Q is right here. Would you accept if I would say that delta y is not equal to, but is approximately dy? It will be. If Q is very, very close to P, they will be. If the difference is just 1, yes. If the difference is 300, no. They will not be the same. But since Q is right here, this actual error, if you want, or change triggered by dx, this is the actual change, will be approximately the differential of y, which will be determined using the derivative, like we did here. That's why this quantity was very close to this quantity. If you remember, this was 0.32, and this was 0.32. No. This was 32, and this was 32.002. So then our conclusion is that delta y is approximately dy. Now, I would like to replace delta y by what we just said it equals to. Here's our delta y. I'm just going to replace it. Can anyone dictate what we replace it with? Delta y. And now we replace the right-hand side. Oh, sorry. The right-hand side is, and we can never forget, and now I'm going to move f of x to the other side. So this is f of x plus dx is approximately f of x plus f prime of x dx. This is a very important concept. And I will show you in a minute how we use it. Before we apply this in any situations, I would like you to see the difference between when we're asked to, so let's say we have, I'm going to say f of x equals 2x squared minus 4. I just picked a function. Can anyone dictate f prime of x?
4x.
Perfect. But now when we're asked to find dy, not dy over dx, this will be the same with dy over dx. But when we're asked to find dy, we have to write f prime of x dx, which is 4x times dx. Please understand the difference between these two. So when we are given a function and we're asked to find its derivative, the derivative is either dx, dy over dx, or 4x, or f prime. But when we're asked to find the differential of y, we have to remember it's f prime of x dx. So understand the difference between these two. So it depends on what we're asked. If we're asked to find the function, the derivative, then it's f prime, nothing else. When we're asked to find dy, then it has to be f prime of x dx. And we'll see all this again coming back in chapter 5. So careful on this. So now let's use this concept. Here's what I would like to say about the concept, what it really means. F is a function, right? So f of whatever x plus some change f of x plus its little change is approximately f of x plus a little change in y. This is dy. So f of x plus its little change is approximately f of x plus a little bit of y, or the change in y. So now, here's how they calculated, let's say, 1 over the cube root of 999. There were no calculators at that time. So how did they calculate this? Well, I'm going to write this formula or concept, x plus dx approximately f of x plus f prime of x dx. And I'm going to identify this, and identify this, and then I'm going to get a very simple expression using the expression on the right. Okay, so let's look at our situation and decide which function we are looking at. Yes, please, Tom?
X to the negative 1/3.
Perfect. This is indeed the function, or 1 over the cube root of x. Awesome. Then let's think what x is. Because you can say, oh, I know the cube root of 8. But from 8 to 999 is a huge distance. I can't use the concept. So there must be something closer that I can take the cube root from very easily.
900?
No?
1,000.
1,000. Right? If x is 1,000, can anyone give us dx, which has to be tiny, preferably under 1, for this to be working properly, for the symbol? What is dx in our case? But negative, right? So x can be positive or negative. So I can have dx on the left-hand side or on the right-hand side. Doesn't matter. So do you agree with this so far? So obviously we have x to negative 1/3. Obviously x is 1,000. Obviously the minor change is negative 1. Agreed? I also need to calculate now, after I determine the function, identify the function, I have to determine f prime. No problem. F prime of x is negative 1/3 x to which power? Negative 1 over 3 minus 3 over 3, which is negative 4 over 3. So this is negative 1 over 3, the cube root of x to the 4th. And I would like to simplify that. And I'm changing it into x cubed and x, so I can simplify it. So what do I get? I can take an x out of the cube root. So negative 1 over 3 x times the cube root of x. Okay, so now I can put everything together. Meaning 1 over the cube root of 999 is approximately what?
Uh, 1,000.
So this is 1 over the cube root of 1,000, because it's the function. I have to plug in x in the function. And then plus, well, it's going to be minus, but I'm going to write plus for now.
1 over 3x.
1,000 times the cube root of 1,000 times dx
Negative 1.
times negative 1. Of course, you know I always run out of room, so I'm going to put here mine times negative 1. So how much is the cube root of 1,000? Good. So this, now I can write the equal symbol. I cannot write the equal symbol between this side and this side. But when I continue on this, on the right-hand side, I can write the equal symbol. 1/10. So I have a negative. I omitted to write the negative in front. Sorry about that. There is a minus here. So negative 1 times negative 1 will be positive. And 1 divided by, so again, this is 10. So this will be 30,000. I need the least common denominator, which is 30,000. And here I have 3,000. And plus 1 is 3,001. And this is a super accurate approximation of this. And you can say, show me. And I hope I'm ready. No, I'm not. So let's check. So we have 1,000. No, I'm sorry. 999 raised to, in parentheses, negative 1 divided by 3. And this is the answer we get taking the cube root of 1 over 999. And then we had 3,001 divided by 30,000. Would you prefer, of course, we have calculators, but would you prefer to take the cube root of 999 and then 1 over? Or calculate 3,001 over 30,000? Okay, so let's take a look at another example. You can choose if you want. We are on page 255. Okay, let's look at 27. Or you can make a problem up if you want. Before we continue, do you have any questions for me here? Any questions? Okay, so we want to, this is our left-hand side. There is a function, there is an x, and some minor change, which is approximately f of the x plus f prime of x dx, which is a change in y, using the differential of y. Okay, so I need to identify, let's write it one more time here. F of x plus dx is approximately f of x plus f prime of x dx. Okay, so now let's identify three things, and they are definitely the function. Which function are we looking at? Mind you, no one can determine this by hand. If this one we can somewhat, this absolutely not. We will be able to determine it very easy. So we need to identify the function. Which function is this? Good. I need its derivative right away. Secant squared, yes, remember? Yes, remember tangent and secant go together. Secant squared x. I need to identify x, and I need to identify dx. So, of course, x should be something I know a lot about. So what will that be? 45 degrees indeed. And what is dx? Perfect. So I can start. I can say already that tangent 44 degrees is approximately, what do I have to write? Let's write it out. Don't calculate anything for everyone to see. Which is? Good. No plus.
Secant squared.
Very good. Very good. Careful. We cannot have degrees here. I can have degrees inside the trig function. That's not a problem. But I cannot have degrees here. So degrees must be changed. Must be changed into. So let's do that. Let's refresh our memory. pi radians is 180 degrees. So 1 degree will be, instead of 180, I want just 1. What do I have to do to both sides to get 1 here? Very good. So this is pi over 180. So now I can continue, and this time I can write the equal symbol because I'm evaluating this. Tangent 45 is the only angle whose sine and cosine are identical over the square root of 2 over 2, which is 1, plus secant 45 is 1 over cosine 45. Yes, yes. So then so let me show you that. So cosine 45 degrees is the square root of 2 over 2. And if you don't rationalize it, is 1 over the square root of 2. I'm sorry, I meant to write secant. Secant 45 degrees is 1 over cosine 45 degrees, which is the square root of 2.
Yes.
So then I have to square it. What do I get? 2. So 2 times negative 1, so it's negative 2 times pi over 180. I will simplify and I get 1 minus pi over 90. So tangent 44 can be very nicely approximated with 1 minus pi over 90. So let's do that. Everything okay? Okay, so tangent, make sure that if you put 44 in there, make sure that the mode is in degrees. Okay, here it is. And now 1 minus pi, no, not that, this, divided by 90. So 0.96509. Is there anything else that you would like to approximate using differentials? That's what we are doing here. We approximated values of functions using differentials. Would you like to choose another example? Or you are convinced that for a minor change in x, we can evaluate anything? Do we need another? Say it again. Yes, let's do one more. Perfect. Do you want to make one up? Let's look at the end of chapter. Let's see if they have anything in there. Or you can make one up. Let's make one up. I can't find any.
Can you find irrational numbers?
Yes, anything.
The cube root of 80 or something like that?
So you want, we did the cube root, so let's find something else.
What about pi?
Well, so, but we have to come up with a function.
Right. Or e.
Yeah, let's try E. I see that. I see one. 24 on page 255. E to negative 0.015. So we know that f of x plus dx is approximately f of x plus f prime of x dx. The starting point is we have to identify 3 quantities, or 3 entities if you want. What is the function? How much is x? This is a minor deviation from
Almost 20.
it's a minor deviation from 0. So what is dx then?
Minus 0.015.
Very good. I have to find f prime. I have all the rest. So f prime of x is? We know f prime. Good. So now we're ready to write e to negative 0.015 is approximately. Let's write it with no calculations for everyone to see, and then we'll calculate.
So, F of
Which is? We only have numbers now.
X is 0. So it's 0.
Okay, very good. Plus.
E to the dx is negative.
So first I have this, and then multiply by negative 0.15. Now I can write equal symbol. How much is e to 0? So the answer is 0.9. So I have 58. Any questions? Okay, so let's look at e raised to negative 0.015. Let's see what we get. And 0.985 is what we got. Convinced that we can approximate anything? That it has a minor error in x? Okay, very good. Any questions? Any questions? Okay. Let's look at further applications of this. And let's look at evaluations of delta y and dy first, and then word problems. So let's say problem 17 on page 255. We are given y, which is the square root of 3 plus x squared. We are given x equals 1. We are given dx equals negative 0.1. They're asking us to find dy and then evaluate it for the given values. When we're asked to find dy, we have to write what formula?
F of prime of x times dx.
Perfect. So this is not dy over dx. It's not f prime. It's not y prime. Perfect. So then I have 1 divided by 2. Please commit to memory the derivative of a square root of a function times the inner function prime times dx. So when we differentiate the square root of a function, we have 1 over 2 the square root times the function prime. I will simplify. So then the simplified form, you can write it as x dx divided by the square root of 3 plus x squared. Or you can leave the x at the end. Both are acceptable. So now we can go in and plug in the information. So we have 1 times dx, which is negative 0.1. And the denominator is 3 plus 1. Square root of 4 is 2. So this is negative 1 divided by 20. So we can say that for this particular function, a change in x of negative 0.1 triggers a differential in y of negative 1 over 20. Let's look at also an example in which we are only asked to find the differential, not evaluate it. Any questions on 17? Is this okay? Yes? Any questions? Okay, so let's look also at, let's say 11. We have y equals x squared sine 2x, and they're asking us to find dy. We're not asked to evaluate it, we're only asked to find dy. So, dy will be, can anyone dictate? And in order not to forget this important piece, since it is a product, since I have to write a lot now, I shouldn't say a lot, but I have to be careful, and it has to be a sum. And I can't forget dx, because the differential means f prime of x dx. Okay, perfect. So I differentiate this, and I get 2x sine 2x plus times 2x times the inner function prime, which is there is no need to factor out 2x. If you want, you can, but there is no need. This is it. Say it again. Everything okay? Can we look at word problems now? Any questions here? So the first function prime times the second function plus the first function times the second function prime times the inner function prime, so I put the 2 in front. Because I didn't want to put it behind cosine 2x. Okay, so let's look at a 35. This is a real application, real life situation application of differentials. So let's read the problem together. The circumference of a sphere was measured to be 84 centimeters with a possible error of 0.5. So from this first sentence, what is 84 and what is 0.5? 0.5 will be dx or dc, this change in the circumference. And 84 is the x, right? Which is in this case, the circumference. Very good. Use differentials to estimate the maximum error in the calculated surface area. And then what is the relative error? And use differentials to estimate the maximum error in the calculated volume. And what is the relative error? Okay, so let's take notes now. So we are told that the circumference is 84 centimeters. We are told that indeed DC equals 0.5 centimeters. So this is like the x in the previous problems, and this is like dx in the previous problems. I have to refresh your memory on some formulas here. The circumference is 2 pi times the radius. The volume of a sphere is 4 pi divided by 3 r cubed. And look how nice the area, or the surface area, is the derivative of the volume. Can anyone give us the derivative of the volume?
The 4 pi.
Very good. So very easy to remember. The surface area of a sphere is a derivative of the volume. But you have to remember that at least the volume. Okay, so let's see what they're asking us to do. Let's read the problem one more time. We established the relationships we need. And now we want to read it one more time. And this is the first part. The circumference of a sphere was measured to be 84 centimeters with a possible error of 0.5. Use differentials to estimate the maximum error. So when we say that this is the error in x, when I'm asked to estimate the maximum error in the calculated surface area, what am I asked to find? So if the error, yes, I'm asked to find dA. So dA is the error in the area triggered by an error in the circumference. So if this is dx, then this will be dy. Okay, so let's start. We have the surface area, and we want to differentiate it, but we want to find its differential. Now, I do have a problem. You don't have to write this. I'm going to write it to explain what I'm doing. So if I write dA, I will have to write 8 pi times r times dr. I don't have r, I don't have dr. So I would rather from the very beginning do something about this r, because I am given c and I'm given dc. I'm not given anything about r. So from here, I will solve for r and plug it in the area before I find dA. So I don't have to worry about r and dr ever again. Is that clear what I'm trying to do? Because I can't use r. I have no information about dr. Okay, so from here, r equals c divided by 2 pi. Therefore, the area becomes 4 pi times c squared over 4 pi squared. So in the area, I replaced r by c over 2 pi, and I had to square the top and I had to square the bottom. I will simplify. So then the area becomes c squared over pi. Or better, 1 over pi times c squared, because 1 over pi is a constant. So now I'm ready to determine dA. So let's find the differential of function a. And remember, I cannot forget to multiply it by dc, because it's a prime times dx, but in this case is dc. Very good. So what is a prime? 2 over pi multiplied by I bring 2 down, I subtract 1 from the power. Is this okay? So the variable instead of x is c. So I have 1 over pi times 2 times c times dc. Now I calculate 2 over pi. I have c, which is 84. I have dc, which is 0.5. So 2 times this is 1. So this is 84 over pi. So let's determine this. 84 and divided by pi. What do I get? 26.738. 26.738. Without measurement unit, it means nothing. What is the measurement unit for this?
Centimeter squared.
Thank you. So let's make a conclusion here. If the circumference happens to be 84 with a tiny error of 0.5, that tiny error of 0.5 creates an error, an estimated, not exact, because I'm using differentials, an estimated error in the surface area of the sphere of how much?
Plus or minus.
It could be because it doesn't have to be positive. The error can be negative, yes. 26.738 squared centimeters. Any questions? Okay. Now we're asked to find the relative error. The relative error has no measurement unit. The relative error is the error in A over the original. In our case, I am going to copy dA, which was 2 over pi times c times dc. You can say, plug in the number. Yes, I just want to show you something. And we can. We will in a minute. Over A, which is 4 pi times I'm going to copy just this. I don't need to copy anything else. It's already simplified here. So 1 over pi times c squared. I'm going to erase the 4 pi. I had it right here under my nose. I copied it from above. Good. So after I simplify a c with a c from the top and 1 over pi with 1 over pi, I get 2 dc over c. So what does this mean? And then we'll calculate it. What does this mean? It means that the relative error in the area is twice as much as the relative error in the circumference. The relative error in the area is twice, after simplifications, the relative error in the circumference. And now I can calculate it as 2. I have dc, which is 0.5. I have c, which is 84. So this is 1 over 84, whatever that is. And I need to calculate because I can also present the percentage error. So 1 divided by 84. So it's 0.0119. 0.0119, so approximately 1.2%. So a minor error of 0.5 in the circumference of the sphere creates a 1.2% error in the area. Now let's repeat the process for volume. How will you repeat the process for volume? Let's think. Where do I start? I have to write. Yes, we have to repeat the